All right, 6.3, binomial radical expressions. So we're going to be doing some arithmetic with radicals, and then we're going to jump into the binomial two-term part. So first, what is a like term? This goes back to Algebra 1. What is a like term, or even pre-algebra, to be honest? So a like term has the same variable and the same exponent. So some examples of like terms are 5x and 3x. We can add those together because they both have x to the first. We add the 8 and the 3. I just wrote an 8. We add the 5 and the 3 and we get 8. Another example of like terms would be 5x squared and 3x squared because they both have x with an exponent of 2. So we add the number in front and the variable and exponent stays the same. Now, we can introduce multiple variables and exponents. As long as they are the same, then these are like terms and we can add those numbers in front. Okay, so then the question that we're answering today, that is Algebra 1 review but not pre-algebra review. What is a like radical? So when can I combine things that have radicals? So adding and subtracting radicals is very similar to adding and subtracting variables. So a like radical has the same root index. We talked about that. Whoops. Hold on, I can't talk and write at the same time. We talked about that last time. And the same radicand. So remember, the root index is the square root, cube root, fourth root. It's the 3 or the 4, the little subscript in the root. And then the radicand is the number under the radical sign. So let me give you some examples. 5 root 2 plus 3 root 2. The root index is the same. There's a square root. It's invisible, but it's there. The root index is the same. And the radicand is the same. The 2 underneath. So when I have those two things the same, I can add these together just like I did with the like terms above. The 5 plus 3 makes 8. And then the square root of 2 stays the same. So I can say something like 5 times the cube root of 2 plus 3 times the cube root of 2. My writing is getting messy. Since these have the same root index and the same radicand, I can add them together and get 8 times the cube root of 2. So let's look at some examples. I'm looking for whether or not they're like terms. These guys are like terms, so all I have to do is 7 minus 4, and then the radical stays the same. Okay, now here, these are not the same. One of them is a cube root and one of them is a square root. We can't do anything with those. They're not the same, so we can't simplify. So just to give you an example of unlike radicals, okay? So this one, in C, they have the same root index and they have the same radicand. There's an invisible 1 in front of that. Remember, we know this from Algebra 1. There's an invisible 1 in front of that, so maybe off to the side, right, that we did 17 minus 1 to get this answer. So the trick is, just like before with like terms, we're subtracting the coefficient, but the radical stays exactly the same. Okay? Let me scroll up and show you what I'm talking about here. So the x in this didn't change. It stayed x. We just added 5 plus 3. The x squared didn't change. It stayed x squared. We just added 5 plus 3, and so on and so forth, okay? So that's what I'm talking about. Now, for D, you might be tempted to say we can't simplify it, but we got to think back to what we've been reviewing. Can we simplify the square root of 75 on its own first? And can we simplify the square root of 48 on its own first? Yeah, we can. Remember, we're looking for perfect squares. We don't want to just know anything that multiplies to make 48. We want to know perfect squares. So let's start with the 75. I know that 75 is 25 times 3, and there's a perfect square in there. Now with 48, it's a tricky one. We want to think of the largest perfect square. You might think 4 times 12, but then you're going to have to do more work because you're going to have to simplify the 12 down into 4 times 3. So instead, let's use 16 times 3. That's the largest perfect square that goes in. Now, stop when you're doing these and make sure you're taking the perfect square out. A lot of people take out the 3, for example. I don't know the square root of 3. Well, I actually do because I'm a nerd, but without a calculator, most people don't know the square root of 3. I do know the square root of 25 though. So I'm taking the square root of 25 and I'm leaving the 3 alone because I don't know the value of the square root of 3. It's not a perfect square. And I do know the square root of 16 and I'm leaving the 3 alone again. And now they are like radicals. So I can do the subtraction. There's an invisible 1 in front of that. I'm just saving my ink in quotation marks. There's an invisible 1 in front of that. Okay, 5 minus 4 is 1. So on this one, I'm going to highly recommend, like I did before, that you write your list of perfect cubes. 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, and I don't think we're going to have to go any further than that. Sometimes you might, okay? So we want to ask ourselves, is there a perfect cube that goes into 250? Well, yeah, I think we can see, right? So we're going to go 125 times 2 plus, is there a perfect cube, one of those things from the purple list that goes into 54? Yeah, I think we see that it's 27 times 2 plus, is there a perfect cube, something from that purple list that goes into 16? You might notice that all of these perfect cubes are being multiplied by 2. And you'll see why that's important later if you don't see it now. So now what did we say? 125, count them out. 1, 2, 3, 4, 5. 125 was 5 cubed. So the cube root of 125 is 5. 27 was 3 cubed. So the cube root of 27 is 3. And the cube root of 8 is 2. That's a messy 3. Sorry about that. So now these are all like radicals. So I can add the coefficients. 5 plus 3 plus 2. 5 plus 3 plus 2. Oops, I changed a plus to a minus, a minus to a plus, didn't I? Let me fix this, sorry. This should be a minus. You've probably been screaming at me the whole time. So we're doing 5 plus 3 minus 2. So that's going to be 6. 5 plus 3 minus 2. And remember, the root stays the same. Nothing happens to it. Okay? All right, let's do some multiplying. Here's where we're going to see the binomials. 2 terms. Terms are things that are separated by addition or subtraction. So we've got 2 terms times 2 terms and 2 terms times 2 terms. We're going to treat these just like we did when we were multiplying binomials with variables. We're going to FOIL. So we're going to go first times first. That's easy. And then outer, we're going to multiply 3 times 4 rad 5. So we can multiply the 3 times the 4, and then the rad 5 is just hanging on for the ride. Okay? Same thing with the inner. we're going to multiply 2 times 2 rad 5. So the 2 gets multiplied by the 2, and then the rad 5 is just hanging on for the ride. Notice that if the number doesn't have a radical, I'm multiplying it by the number that doesn't have the radical. Okay? Now, when we're multiplying, I'm going to write this in a different color down at the bottom. When I'm multiplying last times last, I multiply the 2 times the 4, and then the rad 5 times the rad 5. So I multiply the number that's not in a radical times the number that's not in a radical, and I multiply the number that is in a radical times the number that is in a radical. Okay? So, and then that just ends up being 8 times 5, so that's plus 40. And then I can combine like terms. These ones are like radicals. So I can add the coefficients. 12 and 4 makes 16. And then 6 plus 40 is 46. All right. One thing I want you to not do, I'm going to write this in red. We cannot combine these. I guess you can't really tell the difference much between the red and the pink. We can't combine 46 plus 16. The 16 has something attached to it. We can't combine those, okay? All right, so I want you to try G on your own, and then I'm going to show you the work. Okay, so you might have skipped the outer and the inner because you might have seen that that was going to cancel out when you did FOIL, but hopefully you got this, okay? All right, so let's talk about rationalizing the denominator. This is also Algebra 1 review. So we need, when we're not allowed to have radicals in the bottom, right? We talked about that, I think it was last time. And when there's addition or subtraction, notice this is different than last time. Last time we just had a single thing in the denominator. This time we have two terms. When there's addition or subtraction, we need to multiply by what's called the conjugate. So you might remember from Algebra 1, the conjugate is just changing the sign in front of the radical. So instead of rad 3 minus rad 5, we're doing rad 3 plus rad 5. Okay, so on top I'm going to distribute. So I'm going to do, let me change my color. Okay. 2 rad 7 times rad 3. And I multiply the radical with the radical. So that's 2 rad 21. And then I'm going to do 2 rad 7 times rad 5. And just like before, I multiply the radical with the radical. The 2 doesn't have anything to multiply by, or you could think of it as being multiplied by the 1 that's in front of the rad 5. So that's plus 2 rad 35. And then I'm going to FOIL on the bottom. So first times first. Now, hopefully you recognize that outer and inner are going to cancel. But you might not, and that's okay. And then last times last. Now you're like, why did that help us? Just wait. Remember, our goal was to get the radicals out of the bottom. So the outer and the inner cancel. You don't need to write those terms if you recognize that. And then watch. Lo and behold, the radicals are gone. That's the magic of the conjugate, okay? So 2 rad 21 plus 2 rad 35 over negative 2. I'm going to divide everything by negative 2. Now, you probably aren't going to show this work, but here's what I want you to understand. When you cross things out, we need to cross out from both of the terms, because technically what we're doing is we're factoring out a 2 from the top and then reducing it because there's multiplication going on here. And then this obviously means division. Multiplication and division undo each other, right? So we can cross that off. We've got a negative on the bottom. So I'm going to write it like that. Alrighty, see you next time.